this computer. Okay. From the last semester to this week, I believe that we've been going through a series of talks related to measurement-based quantum computation. And roughly what we've been trying to do is make some connections between MBQC on one hand, on the other hand, contextuality, and non-locality and things like this. And then at the same time, we've also been trying to make some connections to topology. So in the first week, we talked about MBQC sort of in the general format, and then we also talked about different forms of describing contextuality. There's the sheaf theoretic approach, there is the cohomological approach, and then there's also the simplicial approach. And so some of those have some direct connections to topology. So today we're going to continue talking about those general sorts of connections. So let me bring this up here. Okay, so last week, Igor talked about the cohomological, and let me just make sure my volume is on in case you have questions. So last week, Igor talked about the cohomological approach to MBQC, and so we're going to be building off of that. So if you have questions and you missed last week, that's okay, you can ask, but I will be assuming at least some amount of familiarity with the subject matter. One moment here. I want to open another tab. Okay, it's not here, I guess. Anyway, so I will not have a chance to look at this. My apologies, one moment. Okay, there we go. Okay, so just a little bit of background. My apologies for the delay there. I kind of needed to see some of my notes. So what I want to talk about is that in general, we want to think of a situation where we have some observables. So typically we're thinking of quantum observables. So we have a set, which is a subset of all quantum observables, which are a subset of quantum observables. Acting on, which are operators acting on a Hilbert space. Something like this. So one of the things that's going to be sort of background is this idea of a non-contextual value assignment. So a non-contextual value assignment is going to be given by a function lambda going from my set of observables to perhaps something like complex numbers. And so what do I have in mind? What I have in mind is something like I have the eigenvalues of an operator. So the eigenvalues of the Pauli spin matrices are, for example, plus or minus 1. So we want to think of a non-contextual value assignment as sending a operator to one of its eigenvalues. So, we can also, instead of the eigenvalues, we're usually going to be dealing with operators that have eigenvalues plus or minus 1, like Pauli operators. In this case, we can think of instead of mappings S instead of lambda. Lambda is the eigenvalue. Instead, we can think of, 0 to 1, or I can just write this as Z2. That is, we can think of for every for every observable A, which has some eigenvalue plus or minus 1, we can instead write it in terms of its S of A, which is going to be 0 or 1. So where A is an element of the observables. So it's just easier to work with zeros and ones instead of plus or minus 1. So an example of so trying to impose a non-contextual value assignment can be seen from this example that Igor mentioned last time, which is the Merman star. So suppose that you have a set of observables where you have 3 qubits, and you can measure the Pauli X or Pauli Y for every qubit 1, 2, or 3. And suppose that you have a state GHZ, which is equal to, as standard, 0, 0, 0 plus 1, 1, 1. And then you have the fact that you have these eigenvalue relationships, x1, x2, x3, GHZ is equal to minus x1, y2, y3, GHZ equals minus y1, x2, y3, GHZ, and also just give myself some more room, minus y1, y2, x3, GHZ. Now, what is a non-contextual value assignment here? What I want to do is take for every observable that I have in here, for every observable that I have in there, I want to assign some sort of value 0 or 1 in a consistent way. So, for example, I have that if I assign some eigenvalue to x1, x2, and x3 for this relationship here, I would have lambda x1, lambda x2, lambda x3. This property that it will be equal to precisely 1. So I can write it like this, or equivalently, I can write it as the sum of the exponents, s of x1 plus s of x2 plus s of x3 is equal to 0, because the exponent -1 to the 0 is equal to 1. So we can also write the other relationship similarly, x1 plus s of y2 plus s of y3 equals 1, s of y1 plus s of x2 plus s of y3 equals 1, s of y1 plus s of y2 plus s of x3 also equals 1. Now, the common sort of trick that we have to do here is to know 2 things. Twice any sort of, so if I have some number A, which is 0 or 1, then twice this number for either whether it's 0 or 1 is equal to 0 mod 2. So using this identity, if I sum all equations, what I get is the following. Everything here appears twice. This one appears twice. This one appears twice, so on and so forth. They all appear twice. So basically I get 0 equals to the sum of the right-hand side, which is equal to 1. Therefore, if I impose a non-contextual value assignment, it leads to a contradiction. Okay, so we have a couple more strands of things that I want to connect here. So we remember from a couple weeks back that there are these empirical models. What are empirical models? Just the following. An empirical model is a collection of probability distributions over measurement contexts. And a measurement context, if you recall, is just it's just sets of simultaneously measurable measurements, for lack of a better term, just to give you a quick example to illustrate the point. But we talked about this at some point. The set of contexts for something like the CHSH scenario is XI YJ for I equals 1, 2. So there's 4 altogether. So what does that look like? You have these sort of probability tables, something like this. And one example would, so let me label this. You have like X, X1, X2, Y1, Y2. Okay. And so one example of this is something like this PR box that I've talked about before. Or, so this PR box can't be written as a convex mixture of distributions like the one I'm writing now, which are called deterministic, because in every box they have just 1s and 0s. So you have 2 types of empirical models, ones that are contextual and ones that are non-contextual. And so you can sort of split an empirical model, or perhaps I can just write it like this. Any empirical model E can be written as a mixture of non-contextual empirical models, basically convex mixtures of the deterministic ones, plus some amount of E contextual. And so we want to define this thing called a, so where am I going with this? So I just want to talk about empirical models to give you a broad survey of the sort of connections between contextuality and MBQC that we've talked about already. So we have this thing called the non-contextual fraction. And basically what it is it can be written as something like this. The maximum over all possible non-contextual parts of the empirical model. It's the maximum tau. Basically, what you're trying to do is for any given sort of probability table, you're trying to pick out the maximum amount of it that can be described by these deterministic tables or convex mixtures of them. So that tells you how much of the data can be explained by these sort of classical distributions. And then you have that the contextual fraction is just defined as 1 minus that. So So the reason we would like to sort of eventually make a connection between the amount of contextuality and so something is strongly contextual, sorry. E is strongly contextual if the contextual fraction is equal to 1 or the non-contextual fraction is equal to 0. So let's make the connection to MBQC, L2 MBQC. So let's remember what this means. L2 MBQC is the sort of situation that I will, maybe you have some sort of lattice where each node of the lattice can be thought of as a separate qubit or as a separate party. And the basic idea is that for any given site, you have some observable, some measurement that you can perform there, OI of QI. So there's with the L2 MBQC, it means that there's precisely 2 measurements that you can do at every site. So it could be something like the one given by so QI can be 0 or 1. So I have 2 options here, 0I of 1 and 0I of 0. And these can be Pauli measurements, or they can actually, in general, for MBQC, you will need something more than just Pauli measurements to do universal computation, but it's 2 measurements that you can do at every site. And generally, we want to think of the spectrum of these measurements, so the eigenvalue spectrum of these measurements as being perhaps like this, +1 or -1. We will restrict ourselves to binary outcome measurements that we can take to be plus or -1. And so there's a few ingredients for this MBQC. So you have this input vector, I1 to IM, and I will do a little example, the standard Mermin square example, to just make this a little bit more clear. So these are the inputs. You have for every party, so for every qubit, you do a measurement, you get an output. So for n parties, you get n outputs. I will say outcomes to distinguish from the next sort of ingredient, which is the outcome of the computational output of the whole scheme, which will be 0, 1 to 0k. These are all the possible different measurement combinations. There's k of them. So this is the computational. And in general, what you have is a sort of relationship like the following. The vector O is going to be given by some linear operation Z acting on the outcomes. So this can be like the parity. It can just be summing up all of the outcomes of all the particular measurement outcomes. And then you have that Q is actually what tells you, what distinguishes which measurements will be used. It's a sort of input into your MBQC. You put in an I, but then it can also, Q can also depend on, in general, the previous measurement outcomes S plus something like this. So this is the most general thing that you can write down. I should add a couple of things. We've discussed this before, but this is lower triangular. And this guarantees essentially some sort of causality, just to say that Q, which determines, right, when we look at when we look at this right here, the input Q determines which observable you decide to measure there. But we want this choice to be only dictated by previous measurement outcomes. That's why this should be lower triangular. So we have this theorem. This is due to Rausendorf 2013, and we discussed this paper earlier, but I will just remind you of the statement of the theorem, which is that and if any of this is not precise enough, you can ask me to clarify, but some of this stuff is stuff that we covered previously, so I will just sort of some vague familiarity is assumed, but if you're not sure exactly what I mean, feel free to ask any questions. Let me actually see if there's any questions. Okay, that's good. Let M be in L2 MBQC, which deterministically evaluates a vector of Boolean functions. M. So there's M possible inputs. So we have this function O, which goes from Z to M to Z2. And the important statement is the following: that connects MBQC to contextuality in the deterministic case. If O of I is nonlinear mod 2 in I, then M is strongly contextual in the sense that I defined above. That is to say, the non-contextual fraction for the MBQC is 0. So we have an example that we've explored a couple of different times. This is, of course, the Mermin star. And so we have something like 3 parties in this Mermin star scenario. So just to sort of connect with the picture that I drew above, you have 3 different parties. This is not quite a, and then you have for each one, the observables can be the Pauli X and Y acting on that tensor product of the Hilbert space. So X1, Y1, O2 is an element of X2, Y2. And just sort of actually, if you recall, we had this set of this table that reproduced the statistics of the GHZ state with Pauli measurements acting on them. This is kind of what we have here. And in terms of the value assignments, they have to, the value assignments have to reproduce this table right here. So maybe I will just take this quickly. So we have this sort of table of stuff that needs to be reproduced. And what we noticed before was that we already had the following statement, that this is actually contextual, because if I sum up everything, if I just take the sum, I get 0 equal to 1, which is a contradiction. So we know that this is a contextual value assignment. But we also know the following, that what is the function that's being computed here? we have something like the following. This is 0 of 0, 0. So this is O of 0, 0 is equal to this. Where is this coming from? Actually, let's be a little bit more precise here. So here we have the following in this MBQC. We have that I is equal to, could be one of 2 binary bits. And you have that Q, I will just write it in this fashion, is going to be given by, it's I1 for the first qubit, I2 for the second qubit, and their sum for the third qubit. So that's the first 2 ingredients. So we have this table here. So when the inputs are 0, 0, it means that I measure here, if you look at this, this is 0, this is 0, and 0 plus 0 is 0. So you measure X for all of them. Or if you do 0, 1, you measure X for the first one, Y for the second one, and the third one is also Y. O of 1, 0 is equal to, you measure Y for the first one, X for the second one, and Y for the third one. And then O of 1, 1 is equal to, you measure Y for the first, Y for the second, and X for the third. So we already know that this set of equations yields a proof of contextuality because you have this contradiction, but it also is the output is, if you look at this, this is actually the OR gate, which is a nonlinear function. So here's one example where this theorem above holds that if O is a nonlinear mod 2, then you have that M is going to be something that's strongly contextual, which is precisely what we have here. So another ingredient that we've been sort of building towards during this seminar series is the sort of topological approach. So let's see here. There's a couple of things that I don't want to go too much over this because Igor did go over some of this, but maybe the following picture will be useful for us. Sorry. So just in short, what I kind of want to get is the major sort of ideas of the framework, which is that you have a set of observables. Here you can see that on each, so here you have 3 qubits for the Mermin star as we had before. And so each party can measure X1 or Y1. So you have a set of observables, and what you do is take those and map them to edges in a topological space, here a torus. So you have Y1 maps to an edge of this topological picture. And so we have roughly that measurements go to edges of our topological space. And then you have that measurement context, I'll just say context, go to faces. And how can we see this? What are measurement contexts? These are sets of observables that are simultaneously measurable. So when I look at, for example, any one of these cells in this Mermin square, I see that X1, X2, X3, and XXX are actually indeed simultaneously measurable. So those form a face. And so you can sort of codify all of this stuff mathematically using chain complexes. And then so where do you get the sort of relationship to contextuality? Well, you have these value assignments, which are functions, as you might expect, from the edges to, in this case, Z2. You can make the whole thing a little bit more general than that, but just for our purposes, edges to Z2. And then you have this additional sort of beta function. In fact, perhaps it's worth saying at this point that there's some more topological interpretation here. This is a one cocycle. And then this beta is going to be a function from the faces to Z2. This thing is just to be complete, a two cocycle, in the sense that Igor defined last time. And so, and then also there's the following sort of observation before I want to state some just basic results that you can get, some juice that you can squeeze from this formalism. Say you have some edge, some observable that corresponds to some edge in the topological space corresponds to some observable up to some sign, where T is denoting some an element of one of our observables. It could be one of the it'll be one of the Pauli matrices in the Mermin star example, for example. And so what we have is that when you go from an edge to an observable, you have this arbitrariness of the sign that you can give it. So that corresponds to that, depending on the sign that you choose, it will modify the beta function to go from beta to beta plus a co-boundary term. And this defines in equivalence class beta plus d gamma. Okay, so then we have the following result, which is quite nice, which says that a set of measurements, and this is actually, I should say, this is okay, all from 2017, which is roughly just giving the flavor of the idea, a set of measurements is contextual if this beta is not equal to zero, sorry. It's contextual if this is not equal to zero. So actually, the way that it works out without actually working everything out in this example, if you look at this Mermin square, to each of these faces, you can assign a beta value. It will be here, it's 0, 0, 0, and 0. And in the final interior square, it's equal to 1. So this beta class can be obtained in this setting from summing up all of these betas, summing up the betas for each of the faces, and you get that this is equal to 1. So you have that there is a contextuality Mermin style parity-based proof of contextuality from the Mermin square. And this is the state-independent case. There's also the state-dependent case. So in that case, so if we just look at this picture right here more quickly, the way that it works out is there's a sort of construction where what you want to do is, and I will not go over this too much, but you will collapse this interior context, which is more or less, you collapse this interior context, and then you define a new beta, which is given by essentially summing up. So if I go back here, you look at the eigenvalues of XXX, you pick a particular state. In this case, we could look at, for example, the GHZ state. that I defined above. The eigenvalue of XXX on GHZ is 1. On this one, it's the other way around. 0, 1, 1, 1. So the way that you go to this next step for the state-dependent case is to, like I was trying to say before, you collapse this interior piece, and whatever the eigenvalue of that observable that's on the boundary of this, you add that value to the beta inside of the adjacent triangles. So here you have that 0 plus 0 is 0. Previously, you had 0, but now you add 1 for over here, and so on and so forth. 0 plus 1, 0 plus 1. And then once you define this, this beta psi 2 cocycle on a sort of different, on the reduced complex is what it's called, then you have the following corresponding result for the state-dependent case, which is a set of measurements and quantum state psi is contextual if so it's a very similar analogous result. I won't prove this, just sort of going by example, we can see that there's something similar that's going on here. If you sum up all of the faces here, you see again that the sum of the values of the beta psi will sum to 1, which is not equal to 0. And so you get that the state-dependent Mermin square has a contextuality proof, which is what we already proved up here or more up there. Okay, so there's a couple of comments to be made here. And the following comment is this. The topological so there's basically this formalism for discussing hold on, there's one additional piece of, before I go to this, my apologies. There's one additional sort of result that will be useful for us connecting to MBQC. My apologies, I sort of skipped that part. Set measurements. Yeah, so here is the main. So there's some more stuff that that Igor went over last time, but then more or less this formalism plus there are some additional ingredients about the sets of observables that you want to discuss in an MBQC, the idea of a resolution, which I won't get into, but there's this basic sort of result that one can obtain, which is that the function from the set of the input group to Z2. Now, I didn't define the input group for this, but this is more just to give the flavor of it. We won't need it later, but just to sort of give a full picture of the connection to MBQC. You can have this function, which goes from you can think of it as an input to Z2, as we defined previously. Computed in a given deterministic and temporally flat to MBQC. Just to remind you, temporally flat, I sort of hinted at it before, is just the case in which this Q ingredient, yeah, so this is temporally flat if T is equal to 0, essentially just saying that the inputs deciding which observables to measure does not depend on previous outcomes. That's what happens when this T is equal to 0. Flat is related to the cocycle beta psi via, so you have that the computational input or the computational output is equal to beta psi so evaluated on a particular face. So I think this formula is not particularly enlightening, so I will explain it in a second. More or less, it's saying that the computational output is related to the cocycle beta psi, basically saying that for every face, you get some output, modulo some the dependence on I. So for every input and then restricted to that face, beta psi gives you the computational output. The drawback of this is that beta psi is on its own not a topological sort of invariant. So you have that there's this corollary which sort of makes things more precise. And the basic intuition is the following, just basic idea. Is that if I go back to the Merman star example, the function or, and for lack of a better term, the function and are more or less computationally the same in that they're both nonlinear Boolean functions, and they differ by sort of just a linear offset. So because of this, we want to group these together and say that these two functions more or less have the same computational power. So when you sort of make this relationship, once you sort of identify that there should be this sort of equivalence class based on the fact that or and or and NAND are more or less the same computationally, you can sort of refine this result that was written previously to this, which is written as a corollary in the paper that we're following, which is for each deterministic and temporally flat to MBQC, the equivalence class so again, we are making the following assertion that or and are more or less in the same sort of level of computational difficulty. So when you make this sort of assertion, the equivalence class of computational outputs, the equivalence class O of output functions so it's fully determined in this case by the equivalence class of beta psi, which is more satisfying. Okay, there's a discursion here. We can talk about the probabilistic case if you have a question, but instead we will just sort of proceed to the, sorry, where's my Here it is. We'll proceed to sort of the novel part of the paper, which is, so here I will now go to the comment that I was going to make before. A drawback of this formalism is the restriction to the temporally flat case. Okay, actually, so here you notice that the result that I wrote down had two caveats to it. It was deterministic and temporally flat. The deterministic part can be relaxed, and there's a set of results that you can relate the probabilistic case to contextuality and degrees of contextuality. So you can do the probabilistic case, but the temporally flat, so the adaptive case where it's not temporally flat, is not treated well. So the motivation for the example that we will look at now is as a sort of first pass at introducing some level of adaptivity to the to this cohomological version of MBQC. So yeah, so maybe we just go right into it. So just first, I want to define some of the background stuff here. But remember always that the sort of motivation is that we're going to eventually want to look at adaptivity. And the way that that's going to show up in the example is more or less that we're going to be dealing with controlled gates or controlled measurements. We're just as how a C0 gate you can apply a gate contingent on the outcome of, so you can apply a gate to a second qubit contingent on the state of a first qubit. So you can use a similar sort of idea for introducing some amount of adaptivity into the measurement strategy that, or the measurement protocol for this MBQC. So let's go ahead and just define, we're going to deal with a quantum state that's defined in the following way. So we're dealing with 3 qubits. Zero. And so we have some more things to define here. We have, of course, that the 0 and 1 are the eigenstates of the Pauli Z matrix acting on that tensor factor. V is equal to cosine lambda over 2, 0. Lambda I will define momentarily. So I will be more explicit about this. So we have these 2 additional states that are sort of non-standard. You have nu and omega, and they're related to each other by applying the Pauli X matrix to them. So that will give us sine lambda over 2, 0 plus cosine lambda over 2, 1. And lambda here is equal to pi over 2 minus pi over n. So the way that this scheme will work is that you pick an n between, I want to say it's got to be between 3 and, it's just got to be an integer greater than 3. For 2, I didn't check. It might not work for 2. I don't have 1 second. I can check this easily. For any even integer. Okay, so it does work. So n is any even integer. Very good. So the measurements, so we want to specify what the measurements at each site are. We have that for the first 2 qubits, or let's start with the third one because it's a little bit easier. The observables that you can measure here are the poly X and the poly Y, where the superscript is just to denote that this is on the third qubit. And then for qubits 1 and 2, we have that they can choose between a number, so K. So here I just means one of the first 2 qubits. And here, what is this XK? This XK is the following observable, which is so I will just write it down, is equal to cosine K pi over N. And here we have that K is any integer between 0 and 2n minus 1. So how can you think of these observables? You can sort of think of these as rotated Pauli operators, right? So you are sort of thinking of the block sphere and you have X, Y, and Z, and here you are rotating them on along the equatorial plane. So maybe it's worthwhile to just mention this. So if I have something like this, and I have that up here is Z, here I have X, and then here I have Y. So, and then the equatorial plane is the plane spanned by X and Y. So if this is X and this is Y, these XK operators are in some sense, depending on K and N, they will be in this plane that I've drawn here, but always perpendicular to Z. Okay, so just a couple of things here. That will prove to be useful. And we can show this if you like, but so there's a couple of things that are useful to know. One is that xn plus k is equal to x of minus k. And this is just following from the properties of the cosine and sine function. So when you have n plus k, you plug that into here, and then you use the cosine and sine trig functions, and you can show that this is just equal to x minus k. Another identity that will prove to be useful is that x 2n minus k is equal to, this is also equal to x minus k. Now is that, but 1 second. So this is by a similar calculation, but I am not 1 second. This is making less sense. Okay, I think it might be that this one is equal to xk. Okay, well, we can work it out just in case. So the idea is the following. Maybe it's good exercise anyway. x2n minus k is equal to cosine of k plus, or 2n minus k times pi over n times x, where x is an operator, right? And then sine of 2n minus k pi over n y. So you're going to have something like from the first term, when you expand the sum, you have 2n over n. So this will be 2 pi cosine 2 pi minus k times x plus sine 2 pi minus k. Sorry, this is not quite right. So this is minus k pi over n plus sine of 2 pi minus k pi. Yeah, so you can use some identities here, or you can just remember the fact that if you add by 2 pi and cosine is a single valued function, you can just you go back to the original, and then cosine is an even function, sine is an odd function. So you get that this is going to be just cosine of k pi over n x minus sine k pi over n y, which is equal to x minus k. So I guess it was correct in the first place. Okay, so that's another one. Okay, so what is the measurement strategy that we will use? And keeping in mind that we want to implement some sort of adaptivity. And it's the following. So first, we want to measure the third qubit. I will just say Q3. And so we have that the measurements that we can perform are X3 or Y3. And then there's two possible things depending on which we measure. So if we measure Y3, then what will we do? If the outcome of our measurement is plus, so this is the adaptive part. If the outcome is plus, we want to measure O1 equals xn minus 1 minus k. And actually, we will always measure O2 is equal to xk for some k. In the minus case, we will measure O1 is xn plus 1 minus k, and O2 equals xk. If instead we measured O3 is equal to x3, then we measure O1 is equal to x and minus k, and O2 is still equal to xk, like that. So how can we sort of encode this mathematically? So let's define some operators. We have that tk, tau k, my apologies, is xn minus 1 minus k tensor xk2 tensor p plus, which this is the projector onto the positive 1 eigenvalue subspace of the third qubit. So I will, and then plus x and plus 1 minus k. This is on the first qubit, xk2 tensor p minus. Okay, so just quickly to sort of give you the connection here, if you measure y, then it depends whether you get what you measure for qubits 1 and 2 depends on whether the outcome is plus or minus. How do you encode this? Well, if the outcome is plus, then that means that you measured y, you got the +1 outcome, so you project onto that eigenspace, and then you measure this operator here. If instead you measure the third qubit in the y basis and you instead get minus, then you measure these this observable instead. So that's one piece of it where, and let's just be p plus or minus is 2y1. Oh, sorry, this is y3 eigenspace. Okay, so this is one part of the measurement protocol. Roughly speaking, it's corresponding to this. So if you measure, what happens if you measure y in the y basis? If instead you measure in the x basis, then what you have is you will measure this observable equals x n minus k1 tensor x k2 tensor x3. So yeah, okay, yes. So let's move on. So there's a couple of identities. More or less, what are we trying to do here? Now that we set up our observables and our measurement strategy, we want to make a connection to contextuality. So let's just. So one is we want a connection to contextuality proofs. Namely, does this set of observables and this measurement strategy yield a contextuality proof? That is, do we have something like in the Mermin star example where you assign some non-contextual value assignment and then you run into a contradiction? Two, we want connection to topology / the cohomological framework. So what we want to do is actually do we want to take the first leg of this and sort of establish a relationship to contextuality and then see if we can interpret what we're doing topologically. So to do this, we need to establish some relationships like we had with the Mermin star example. Perhaps it's here. You have something plus something plus something equals something, and then you have a set of equations and you want to run into, if it's contextual, a value assignment, then you will run into some sort of contradiction a la the Mermin star. So let's see how that comes about. First, we need a couple more identities. And I don't want to get bogged down too much in this, but at least just to get the idea of where some of the results are coming from. Let's establish, so we have first this one. Suppose we have xk acting on one of the first two qubits, and it's acting on a 0 or 1, z eigenstate. X is 0 or 1. So what is this going to look like? So this is cosine k pi over n times x plus sine k pi over n times y, and all acting on x. So if you just recall, we have that x acting on a z eigenstate will just give us x plus 1, and y acting on x will give us, I suppose it's -1 to the x times x plus 1. Okay, so when I act x and y on x plus 1, what I will get is so x and y acting on x will give me x plus 1 as the final state. But there will be some phase factor in front of it. So how do we get that? So for the first one, we get just, you'll get cosine k pi over n. For the second one, when you act y, you get this phase factor right here. So this is going to be plus I negative 1 to the x times sine k pi over n. And so we can see where this is headed, because essentially this is just going to give me exponential I negative 1 to the x k pi over n times x plus 1. So that's how the first one acts on, that's how one of these xk's acts on a z eigenstate. So now we also have, we can use this to understand how operators or observables of the following format work. X, call this M2, acting on the first two qubits, call it X. And we can restrict ourselves to the two that have the same, because remember, psi, the state that they will be acting on has, it will be either 0, 0 or 1, 1. So we can just restrict our attention to those cases. Here, X is an element of Z2. So if we just use the properties that we got before, what we have is that this is e to the I negative 1 to the x, because it's the same exact x, L plus M pi over n times x plus 1, x plus 1. So something like this. So you can more or less use this to get some, remember, in the contextuality proofs that we used before, we always had some sort of eigenvalue, some deterministic outcome. So here we want to find out what are the eigenvalues of x, sorry, did I, yes, xk bar, that's correct. So the first one, we will look at xk bar acting on psi. This one is not so hard to compute, so I will just do it so that we get the gist of the idea. X and minus k tensor x k tensor x. So I'm dropping the qubits superscript just to keep things simple, but we're left to right is qubits 1, 2, and 3. Acting on 1 over square root of 2, 0, 0, nu plus 1, 1. We can, and we also, just the identity that we had before was that x acting on nu is equal to w or omega, and x acting on omega is equal to nu. So using that and the identities that we wrote down above, it's not hard to see that we have 1 over the square root of 2 e to the I pi. Where's the e to the I pi coming from? It's coming because if I look at this formula here, I add L and M. Here, when I have n minus k and k, it means that I will have e to the I n pi over n. So I just get e to the I pi. And it's positive because of the way that it works out for the first factor. E to the I pi, and then this one would be 1, 1, and then omega. plus, we also have, from the other side, you will get e to the, because of the fact that there's a 1, 1 here, we have e to the minus I pi 0, 0 nu, which is just equal to minus psi, because of e to the I pi, e to the minus I pi are the same. So that's the eigenvalue for the first one. I won't do the other ones because they're a bit more tedious. This one is roughly the same calculation. We will also need it. E to the minus k tensor e to the k tensor x acting on psi is equal to psi. So that's an analogous computation. Another one, so this one is significantly more tedious, or at least I was not able to get it in a very simple way. So I will defer the proof of it. You can ask me, or you can try it as an exercise for the reader. So this one will be minus psi. Similar, but more tedious. So we obviously now have the following question. Is there rather a non-contextual value assignment that reproduces these statistics, as it were? Yeah, so in order to do this, we're going to use the same simple trick. Recall, so for the Merman star, what did we do? We had, for every observable, we mapped that observable OI to some S of OI, something like this. So this is for the Merman star. We're going to do something similar, and it's going to go as follows. Let AK, or similarly BK, be the outcome when xk1 or respectively xk2 are measured. And so that's for the first 2 qubits. For the third qubit, let C0 or respectively C1 for when, I guess, X3 or respectively Y3 are measured. Okay, so now we want to sort of establish some relationships here. So for from equation A and B, actually, we can go to from the eigenvalue relationships to relationships where, by the way, sorry, I should have mentioned this. AK, BK, CI are all in Z2. So you're taking each of the observables, so basically the xk's acting on each of the first 2 qubits, or x or y acting on the third qubit, and you're going to give it some value. And you want it to reproduce these eigenvalue equations that I have here. The first one, so the first 2, or perhaps I will start actually with B, is that if I have x of minus k and x of k plus x plus C0, this needs to be equal to 0. So from B, we have that AI plus BJ plus C0 equals 0. This is the case when I plus J equals to 0 mod 2n. So from A, we get that AI plus BJ plus C0 equals 1. This is when I plus J equals 2n mod 2n. Where's the 0 and 1 coming from? It's equal to 0 because you get back the original state here, and it's -1 for the second one because you get minus the state. So those are the first two. Then there's when, so this is when, I suppose this is when the third qubit you have that x3 is measured. When instead y3 is measured, things are a little bit more complicated. So let's see here. So this is coming from equation C. And what you get is that AI plus BJ equals 0 if I plus J plus -1 to the C1 equals 0 to n. And instead AI plus BJ equals to 1. Just the I plus J. It's -1 to the C equals. Okay. So the second pair, it's not immediately obvious how to get these relationships, but I will sort of skip the proof. If somebody, if you guys want me to go through it, that's fine. But just for the sake of time, let's just skip this part. And so to show that so that these set of equations yield a contextuality proof, let's restrict ourselves to the case n equals 4. So we have to look at only just the even integers. So when we have n equals to 4, okay, so what I will just write down all of the equations more or less. You can pick out some of the equations. You can trust me when I say that coming from the first set, you have something like A0 plus B0 plus C0 and I will write the right-hand side is just another plus. You can do this when it's Z2. So plus A1 plus B3 plus C0 plus 1. So what am I doing? I'm taking equations from this set and this set as well. So just for, let's see, these equations. Yes, okay, so take this one and then take these sets, the ones that I'm about to write down. A2 plus B2 plus C0 plus 1. And then also A3 plus B1. More or less, all I'm asking is that you believe that these equations are coming from this set right here, right? This is I plus J equals to N. And when I look here, I'm setting N equals to 4, I plus J equals to N, and N. So that's just coming from that set of equations. This one is coming from the first set right here. So 0 plus 0 is 0. Okay, and then we also take from the second set of equations right here, we take, I will try to just be quick about this, A0 plus B3 plus 1 plus A1 plus B2 plus 1 plus A2 plus B1 plus 1 plus A3 plus B0 plus 1. And because I already added the right-hand sides into this, this is all going to be equal to 0. So when you add it all up, so if I take the sum of this, what happens? I can just sort of observe that some things are going to show up twice. A1 here shows up here, and then it shows up here. A2 shows up once here and once here. So I have the two sets of equations, and each of the values are showing up once each time. So I get something that looks like C0 is going to show up 4 times, or n times, for C0 plus 2 times from sum I equals 0 to n minus 1 of AI plus BI. Plus, when you count up all of the these constants, you get 7 mod 2 equals 0 mod 2. We see that this one in modulo arithmetic, you have an even number times C0. This one's equal to 0 mod 2. Similarly, this is also equal to 0 mod 2. So all that you're left with is 7, which this one is equals to 1 mod 2. So you have the contradiction. You have 1 equals to 0. So there is a contextuality proof. That's one thing that we wanted to establish. And now there's something else. We want to also establish a relationship to topology. So maybe I have there's these nice pictures. Yeah, so maybe we can just look at this for a second. This topological picture, where is it coming from? Each of these faces have to do with simultaneously observable measurements. So basically, the whole measurement scheme can be bifurcated into 2 topological pictures, one in which C1 is equal to 0, one in which C1 is equal to 1. That's pretty much the idea. Remember, C1 is the outcome corresponding to when you measure Y. So depending on whether you measure, you get the outcome of the third qubit to be 0 or 1, you have these 2 different pictures in which each of the faces correspond to simultaneously measurable observables. And you can sort of assign beta values like you did before, so you can sort of more or less do the same sort of thing. The problem is that this whole thing hinges on there being a value for C1, that there's a non-contextual value assignment that you can assign in the first place. Remember, that's how you're splitting things up. But we just proved that there's no such non-contextual value assignment. So this topological picture is not really quite correct. So we want to actually sort of refine the picture somewhat. We want to introduce the basic ideas that we want to introduce new observables such that in every face here, so when you just zoom in on this, you will introduce new observables, which I will write down. But the basic crux of the idea is that introduce new observables such that you have these commutation relations, so that, and this defines how you can assemble these things into faces. They have to all commute, they have to all multiply to plus or minus the identity, the observables on each edge of a face. So you have these rules that Igor went over last time for how to assemble observables into this topological picture. And the essential sort of ingredient is that we just need more observables. And these observables are going to have a certain sort of structure. So I will just write them down because we're more or less running up against the end of the time. So this is not a real word, so I don't know how to spell it. So let's just de-iffy it. Okay. I will write this down and at least explain what's going on momentarily. I think it's fair to recall that in our measurement strategy, X, the second qubit always measures, for a given X, it always measures XK. So that's important to remember. The only things that are really being adaptive are the first and third qubits. So you can define these observables that look something like this. Identity on the third qubit plus, so this is actually just, I'm copying it, but there's actually, this is projector onto the positive eigenspace for qubit 3, tensored with xk minus 1 on the first qubit plus, this is p minus for the third qubit, tensored with x k plus 1 on the first qubit. So all of these are just going to be relationships between, they're just going to be controlled operations on the first and third qubits. So this is x epsilon k plus, epsilon k minus. And so let's see if I can write these down more or less quickly. So p plus, and I will, anytime there's a p, it will be for the third qubit. So I'll just drop that superscript. And the other one will be on the first one. So just to give us a little bit of simplicity, plus p minus tensor with the identity on the first qubit. And then this one will be p plus tensored with the identity plus p minus tensored with xk plus 1. And so there are certain commutation relationships and eigenvalue relationships that these satisfy. So you can plus so you need to establish these first in order to know how to assemble things into this topological picture. So where is this coming from? These controlled gates are just telling you, this is kind of like something people are more familiar with. I will just leave it on this. When you have something like the C0 gate, a lot of times people think that this is defined like I0, 0x, but really, abstractly, you would have first think of, so C0 gate acts on 2 qubits such that depending on the outcome of the first one, when you measure in the Z basis, you do something on this, you act a gate on the second qubit. So maybe a priori, the way that to actually write this down is not this matrix, but actually the following thing. You have the the projector onto the Z eigenspace for the first qubit, tensored with what you do to the second qubit, which if it's plus, then you do nothing, plus pi minus of 1 tensored with what do you do on the second qubit in the C0 gate? You apply the x. Sorry, this is 2. This is 2. So more or less, this is like 1 0 0 0 tensored with the identity plus you have 0 0 0 1 tensored with x2. So this is actually how you write these controlled operations, and this is how you introduce some level of adaptivity. That's kind of the same thing that we're doing here. So you can establish the commutation relations, which allow you to sort of assemble things into this topological picture. And I think it's left more or less as an open question. Something that we're hoping to maybe work on going forward is just to see what the principle is here. So this is a particular construction for a particular example where you can go and write down these new observables. Once you do this, you can, sorry, I should have copied this. You can write down a new picture like this so that you have these faces where you have mutually commuting observables, and then you can add these new faces. And everywhere there's a pink, it means that there is a beta equal to 1. Beta, I guess this is the relative complex, beta psi equals to 1 for this face. And you have an odd number of faces. So you, again, reproduce the contextuality proof. And you don't have this bifurcation that depends on the value of, so here like C1 equals, now I'm not sure, but I think it's like this, C1 equals 1. In general, this value C1 might not exist because you don't have a non-contextual value assignment. So you can't condition on this value. And this picture does not require this bifurcation depending on a non-contextual value assignment. So it's a step in the right direction. Introduce new observables, and it seems like these new observables have to be related to the adaptivity in some way. And that's at least a starting point for how to generalize the cohomological framework introduced last time by Igor to introduce to allow for some version of adaptivity. I have not been checking for questions, so I apologize for that. Okay, that's more or less it. If you guys have questions, feel free to ask. Let's see, there are some people here who might want something signed for their class. Not sure how to handle that, but if you send me an email or something, perhaps myself or probably Cihan more likely can sign it and attest that, you know, indeed you were present.
Yes, I can do that. I don't see any anything on chat. So how did people reach you?
So some students sent me an email. So what I just screenshotted the participants, and maybe somebody was here and they left. So I'm sorry. I should have maybe checked beforehand. But more or less, people sent me an email for the link. So if they send, I can actually write my email in the link in the chat. 1 second. So you can reach me at that email, and then so if you attended and you need something signed, I can either forward it or do something. Okay, seems like there's no questions. So I think that's a wrap. So I will talk to you guys next week. We will be shifting to classical simulation as the main priority topic starting next week. So, and the topic will be about the stabilizer formalism.